लक्ष्मीकांत जी शुरू करें। हेलो लक्ष्मीकांत जी।
जी सर।
शुरू करें कि रुक जाएं?
नहीं सर, बिल्कुल शुरू करिए, 10 बज गया है।
ठीक। तो सुप्रभात, गुड मॉर्निंग ऑल ऑफ यू। जैसा कि कल हमने आपसे कहा था कि आज पहला व्याख्यान हमारा है और उसके बाद 11 बजे से डॉक्टर लक्ष्मीकांत का, और तीसरा व्याख्यान 1 बजे से 2 बजे तक रामजी पांडे जी का। कल हम लोगों ने कुछ बातें की थी, एक थ्योरम का भी प्रूफ किया था कि जिसमें दिखाया था कि 5 स्टेटमेंट अलग अलग हैं और वो पांचों स्टेटमेंट इक्विवेलेंट हैं। वहीं से शुरुआत करते हैं और मैं अपनी स्क्रीन शेयर कर रहा हूं। लक्ष्मीकांत जी, स्क्रीन शेयर हो गई?
यस सर।
ओके, थैंक यू। तो शुरुआत करते हैं और एक फॉर्मल डिफिनीशन से बात करते हैं कि व्हेन वी से दैट metric space is connected. So I'm writing here that you can say that it is a definition. A metric space X is called a connected metric space if and only if X cannot be expressed as the union of two disjoint non-empty open subsets of itself. That is, if you are writing X as a union B, so we cannot write X as a union B where A and B both are open in X and A intersection B is phi. If we cannot write X in this way, then we say that X is connected metric space. Otherwise, we say that X is not connected metric space or X is a disconnected metric space. So one remark you can see here that I'm not writing the remark, but I'm just saying that from the statement of the theorem, which we have proved yesterday, we can say that a metric space is connected if and only if it satisfies any one of the criteria listed there. तो जो भी क्राइटेरिया हम लोगों ने 5 अलग अलग क्राइटेरिया लिस्ट किए थे और उन पांचों में से अगर कोई एक भी क्राइटेरिया फुलफिल होता है, तब हम कहेंगे कि हमारा मीट्रिक स्पेस कनेक्टेड मीट्रिक स्पेस है। तो कुछ एग्जांपल्स की बात कर लेते हैं। वी कैन अंडरस्टैंड these things with the help of example. Number 1, suppose our metric space is R with a usual metric, then we will show that it is connected. To consider a subset, a proper non-empty subset, so let S subset, which is a different from phi and which is a proper subset of R, and we are considering a point A belongs to R minus S. I'm just drawing a diagram that will be helpful for you. Suppose it is R and we have like this one beta, and then we have a point x1 and x2, and then we have a point here. Suppose this is a, and considering S as, for the sake of convenience, you can take any set. This is a one example which I want to put here in general. Suppose this one, or you can say that it is x1, x2. So you can take S maybe like this, जिस तरीके से हमने यहाँ पर S लिखा हुआ है वो एक एग्जाम्पल के तौर पर कि आप ऐसे भी S को सोच सकते हैं, S कोई भी, लेकिन जो यहाँ पर हम बात करें that is a abstractly saying that S is a non-empty subset and a proper subset of R. तो कोई ना कोई point R minus S में मिलेगा. Suppose that point is A. Then if the set this one is not empty, then let B be its infimum. The distance ds is equal to 0. This is quite obvious. Then we can say that either B is equal to A or this one is subset of R minus S. Whatever the case may be, either B is equal to A or interval AB subset of R minus 1, R minus S. In either case, distance of B R minus S is 0. So you can say that B belongs to boundary of S. And a similar argument shows that, you can say that a similar argument shows that dibber S is, that is a boundary of S, is not empty in the case when minus infinity A intersection S is different from phi. So this is a one example in which we have proved that R with the usual metric is connected. Then I'm going to define what is a connected subset. So a connected subset of a metric space is a subset that endowed with the subspace metric is a connected metric space. यानी कि कोई भी मीट्रिक स्पेस है X और उसमें एक सबसेट हम लेकर के चल रहे हैं, S is the subset of X, then we can think S as a subspace of X, and as a subspace of S, if it is connected, then we say that S is connected subset of X. We can also see it in another way. For this, we have to first define separation. Now I'm defining what is a separation, and for separation, I'm defining this another way. Let XT be a metric space, and A is a subset of X. A pair of subsets A1 and A2 of A is said to be a separation of A if number one thing is A1 is a different from phi, A2 is a different from phi, and A1 union A2, this is equal to A. Number two, A1 intersection A2 is equal to phi. Number three, A1 closer, that is a can think closer of A1, and A2 bar, that is a closer of A2 in X, और ये किस तरीके का होना चाहिए such that A1 closer intersection A2, this is phi, and A1 intersection A2 closer, that is equal to phi. That is A1 and A2 are non-empty disjoint subsets of A whose union is A, and neither A1 nor A2 contains any limit point of the other. Here we can see all these things with the help of examples. Again, here I'm taking R with a usual metric. Then I'm consider a subset A, open interval, this one, and A1 is suppose taking open interval 0, 1, and A2 is a 1, 2. So we can say that these subsets A1 and A2 do not give separation of A. Here you can say that here A1, A2 satisfy number one, that is A1 is different from phi, A2 is different from phi, and A1 union A2 is equal to A. That's true. And it satisfies two also, that A1 intersection A2 is phi. So this satisfies one and second, but you can see that, but not satisfy third condition. So you can say that it is not a separation. Here also, if we take suppose A1 as a 0, 1 and A2 as a 1, 2, then again A1 and A2 do not give separation of A. Here A1 and A2 satisfy, these are not separation of A. A1 and A2 doesn't satisfy 1. Again, now I'm defining another thing. In the by separation, we can define what is a connectedness. So we can say that let X be a metric space and A is a subset of X, then A is said to be connected if A has no separation. If A has a separation in X, then A is called a disconnected set. We will see more examples here. Number one, that R be the usual metric space, and we are considering that A of R minus 0, that is a punctured real line, can say that. Then we have A1 as this, and A2 is this one, such that A1 union A2, that is equal to A, and obviously A1 intersection A2, that is equal to phi. And again, if you want to see what is the closure of A1, so that is this, and you can find that closure of A1 and intersection A2, so that is phi. So here you can say that R minus 0, that is A, which is not connected. Another example, we can check that. Set of rational number in R, where again I am taking R as a metric space with a usual metric. So this is disconnected. Any guess? For this, we can take any irrational number, like consider A as a set X belongs to Q, such that here I am taking a irrational number root 3. You can take any one. This one. And B as X belongs to Q, such that X is greater than root 3. Here it is quite obvious that here you can say that Q is as A union B. And of course, A intersection B is phi. And the third condition, which we have just seen earlier, that is also correct. So we can say that Q is disconnected in R. Now we will prove a simple result. So you can see here a theorem. Let X be a metric space, taking Z be a subspace of X, and S is a subset of Z. Then S is connected subset of X if and only if S is a connected subset of Z. मतलब कि S connected अगर सुपरसेट में है तो S connected subset में भी होगा. So proof is a quite simple and one line proof I'm giving you. You can say that the open subsets of S is the same whether it is viewed as a subspace of X or of Z. So S is connected in X. This implies and implies pi. S is connected in Z. Now, I'm going to prove another theorem. Next theorem that is important. Let X be a metric space S is a connected subset of X, and there is a set A like this. A S is a subset of A and A is a subset of S closer. Then A is connected. तो अगर जो है X कोई भी मीट्रिक स्पेस है और S कनेक्टेड सबसेट है X का, और कोई एक सेट हमको A मिल रहा है जिसके अंदर S कंटेंट है और वो सबसेट S क्लोजर के अंदर कंटेंट है, तब हम कहेंगे, प्रूफ करेंगे कि A जो है वो भी कनेक्टेड होगा. तो प्रूफ इज अगेन क्वाइट सिंपल, बट it has some line. So suppose if S is phi, if I'm saying that, then again S closer is phi and then nothing to do. Then nothing to do. So let S is different from phi. Now we are considering a function. Suppose f, a function from given set A 2, 0, 1, is continuous, then we are restricting f at S is continuous. और अगर f को रिस्ट्रिक्ट कर दें s पर और वो कंटिन्यूअस है और ये दिया हुआ है कि s क्या है आपका कनेक्टेड है, तो हम कह सकते हैं कि f किस तरीके का फंक्शन होगा. f is a constant function. So we can write here that so f is constant since s is connected. Then for every x belongs to A, we have x belongs to S closer, so that there exists a sequence xn in S that converges to X. And here we are taking f as a continuous function, so we can say that since f is a continuous function, the sequence fxn converges to fx. But here you can see that fxn is a constant sequence, so that f has the same value at x as it has on S. Okay. Here we have taken x arbitrary. You can say that as x is arbitrary in A. This shows that f is constant on A. Again, because f is an arbitrary continuous function, arbitrary continuous function from A to 0, 1. Therefore, A is connected by the continuity criteria, जो हम लोगों ने कल थ्योरम किया था. अब बहुत सारे एग्जाम्पल्स हो सकते हैं, बहुत सारे सवाल हैं जिनको डिस्कस करते हैं, तो कुछ एग्जाम्पल्स की पहले बात कर लेते हैं. तो वी कैन इजीली सी दैट. Remark number 1, every singleton subset of a metric space is connected. Okay, this is a quite obvious. And number 2, every empty subset is connected. और ये दो सबसेट हैं. इनके अलावा अगर हम कोई भी फाइनाइट सबसेट लेके चल रहे हैं, नो अदर फाइनाइट सेट is connected. To see this, we, in my mind, just one question is rising, that are there any other countable connected subset of a metric space? I'm writing the question, that is important. You can think about that. Are there any other countable connected subsets of a metric space. अभी तक हम लोगों ने ये काम किया कि कहा कि कोई empty subset है तो वो connected है, singleton है तो वो connected है, और इसके अलावा कोई भी finite subset अगर है तो वो connected नहीं है. लेकिन अब इसके आगे थोड़ा सा बढ़कर के सोचने की बात है कि अगर हम कहें, सोचें दिमाग में कि कोई काउंटेबल कनेक्टेड सबसेट हो सकता है मीट्रिक स्पेस में कि नहीं. So that is important, and you can think it. Any answer? I'm just giving you a hint. So answer is quite easy, that there are no such metric spaces. कि कोई भी इस तरीके का मीट्रिक स्पेस नहीं होगा जिसमें कि काउंटेबल कनेक्टेड सबसेट हो. ये बात तो सिर्फ मीट्रिक स्पेस के लिए कही जा रही है, एक रिमार्क के तौर पर इसको आप सोच सकते हैं. और जब कभी भी कुछ लोगों ने टोपोलॉजिकल स्पेस पढ़ रखा होगा तो उसके लिए ये बात नहीं कह रहा हूं इन जनरल. तो यू कैन थिंक दैट आई एम राइटिंग इट एज अ रिमार्क इन मोर abstract word of topological spaces in finite connected countable spaces do exist, but in a metric space it is not. I'm going to prove this. So suppose XD be a countable metric space with more than one element. If I'm saying that countable, it means it is counted also. Yeah. So counted is taken in a countable. Some people are just differing it that counted and then countable, but a counted set is also a countable set. Let AB belongs to X with A is different from B. Since the interval I'm taking here, that is 0 and distance of A. Since A is different from B, then distance of AB is always greater than 0. So you can think about this open interval. Then this interval is uncountable. That is correct. Yeah. Then we can say there exists an element in this interval such that no point of X is of distance f from A. Think about that, because you have taken what X as a countable metric space Then if you are taking two elements in X, so what you find that their distance is not then considering open ball just like this, A and I'm taking this one, which is nothing but X belongs to X. I'm just recalling this distance of AX is less than S. And closure of this, and which is a close, that is X belongs to X, such that distance of AX is less than or equal to S. These are same in X. That is V of AS same as this one. So this is both open and closed in X. और जब ये बात हो गई हमारा काम आसान हो गया. Then we can say that, but A belongs to this set and B does not belongs to this, so that this is a proper non-empty subset of X. Okay. Then BAS is a proper non-empty subset of X, which is a open as well as closed. So we can say that X is not connected. Now, I'm coming to some results and some simple proofs of those results. And here I'm going to discuss some relation between continuity and connectedness. We can think about connectedness and continuity. Starting with a simple result, that is every continuous image of a connected metric space is connected. Proof. तो इस रिजल्ट को प्रूफ करने के लिए सिंपल सी बात हम करते हैं और that is we are using this fundamental thing from algebra that P implies Q is equivalent to not Q implies not P. कल भी किसी ने कहा था कि रिजल्ट, मुझे याद है सवाल एक चैट बॉक्स में पड़ा हुआ था कि जब मैं प्रूफ कर रहा था वो 5 इक्विवेलेंट स्टेटमेंट्स वाले, तो 3 implies 4 के प्रूफ के लिए किसी ने क्वेश्चन मार्क किया कि सर ये बचा है, तो वहां पर भी प्रूफ यही किया था कि 3 implies 4 is equivalent to 4 not 4 implies not 3. So both are the same thing. Here I'm also doing the same. So here we are going to prove, let X and Y be metric spaces and f from X to Y be a continuous function. So not Q means what we have to take, Fx is not connected. So suppose this Fx is not connected. Then there exists a continuous function g from fx to the set 0, 1 such that g is not constant. It means g is onto. Okay. This yields a continuous map GOF from X to 0, 1 such that GOFX is 0, 1. Here we have taken f as a continuous function, g as a continuous function. So GOF is a continuous function. So we can write GOF, since GOF is continuous, X does not satisfy the continuity criterion for connectedness, and therefore not connected. So here we have proved that X is not connected. It means every continuous image of a connected metric space is connected. Hence the result. I'm stating one corollary of this result that is important, and can think. Suppose S, which is a non-empty subset of R, then S is connected if and only if S is an interval or singleton. तो अगर जो है यहां से हमें ये बात पता लगती है कि अगर S जो है कोई भी सबसेट है R का और S कनेक्टेड है, तो S या तो एक इंटरवल होगा या सिंगलटन होगा, इसके अलावा कुछ और नहीं हो सकता है. So we will show this result. Suppose S is not an interval, then we will see what happens. Then there exists X naught belongs to R with x naught is a greater than infimum of S and supremum of S, such that x naught does not belongs to S. So S intersection this one and S intersection this one are non-empty. Open subsets of S. And you can see that. And what happened here? And if you are taking union of all these S, this one, union, this one as S. So we can say that S is not connected. If S is not an interval, then S is not connected. Means S is a connected, then S is an interval. And for converse, you can see that since R is connected, and we know that continuous image of a connected set is connected. So every interval is connected. Last I'm going to, this is the last corollary which I will prove here today. So next corollary, which is again based on the previous theorem, and all the people know this as a result, which is known as intermediate value theorem. So I'm just writing that is, let X be a connected metric space and F from X to R is continuous. Suppose alpha belongs to this interval infimum of fx and supremum of fx, then there exists z belongs to x such that fz is equal to alpha. So proof is quite obvious. Number one thing is, if f is a constant function here, then the result is obvious. We can write if f is a constant function, then the result is obvious. If not, So since it is given that X is connected, so this implies that what? Since f is a continuous function, then fx is connected. And if fx is a connected, then we can say that since fx is a subset of R, so it is either singleton or it is an interval. So we can say that fx is singleton or fx is an interval. और इन दोनों केसेस में हम कह सकते हैं in both cases alpha belongs to fx. So this is all for today. Thank you for listening me. Any question or any doubt? You have 1 or 2 minutes more.
Sir, there is a doubt from Ajay Yadav.
Yeah.
Is any separation exists in this space?
Which space?
I don't know. He is writing only this.
In this space, if you are taking R as a usual metric space, then I have already proved that it is connected. In R2, if you are taking as a whole space, then it is also connected with the usual metric and R3 also. Yeah. But there are many subsets of R which I have taken today, which are not connected, which are disconnected. So you can see it. And if you have a larger question, then write it properly and then you can ask another day also. Thank you. Any other question, Ramji? No. So it is time and 2 minutes more. After 2 minutes, we will meet here. और आप लोग अपने आप को डिस्कनेक्ट मत करिएगा और इसके बाद जो है डॉक्टर लक्ष्मीकांत मिश्रा जी अपना लेक्चर देंगे. लक्ष्मीकांत जी?
यस सर।
हाँ, शुरू किया जाए।
श्योर सर, शुरू करते हैं।
तो हमारे बीच में डॉक्टर लक्ष्मीकांत हैं और हम उनसे अनुरोध करते हैं कि वो आज अपना व्याख्यान शुरू करें। डॉक्टर लक्ष्मीकांत।
ओके सर, थैंक यू सो मच सर। तो पिछले लेक्चर में हम लोगों ने कुछ चीज़ें करी थी, जिसमें हम लोगों ने बात किया था कंप्लीट मैट्रिक्स स्पेस के बारे में। तो मैं स्क्रीन शेयर करता हूं क्योंकि आज मैं बोर्ड पर नहीं लिख पाऊंगा। Is the screen visible?
Yeah,
Okay.
quite visible. Good.
Okay, sir. So let me start about completeness. We started from sequence of metric space, sequence in metric space, and then convergence sequence. It is convergence sequence, Cauchy sequence. It is already done in previous lecture. So we have also observed that every convergence sequence in a metric space is a Cauchy sequence. We have already observed, and and I asked the question that is the converse of above proposition true? So that means is every Cauchy sequence convergent? So answer is what? Answer is no. And we have seen the example that the sequence 1 by n in the open interval in open 0 closed 1 with usual metric is Cauchy sequence, but it is not convergent in this open 0 closed 1. Okay. Similarly, we have seen these two examples also. Now, for a minute. Okay, so we have discussed that the definition of complete metric space, that a complete metric space is what? It is a space in which every Cauchy sequence converges in that space. Okay, and that metric space which is not complete is called incomplete metric space. We have seen these examples in previous lecture, that every discrete metric space is complete, and metric space R with usual metric is also complete, and Rn is also complete. The next example is what L infinity, we had already discussed it. This is the collection of all bounded real sequences, and it is complete with the metric defined here. Okay, and next example is C01. That means set of all continuous functions from closed interval 0, 1 to R. Okay, and if we take D, metric function D, defined by integral 0 to 1 mod fx minus gx dx for every f and g. So this metric space is not complete. That means it is incomplete metric space. Why it is incomplete? We can construct an example in this metric space which is Cauchy sequence but not convergent. Okay, so uh, consider this sequence of functions defined here. F1, what is F1x? This is 0. Wait for a minute, I should not note it here. Okay, so what is F1? F1 is this one. Uh, okay, F1 is this one, and F2 is what? F2 is 0 between 0 to half, and between half to 3 by 4 it is 2x minus 1 multiplied by 2, and after that it is 1. Okay, so similarly we can define fnx, which is 0 from 0 to half, and within half to n plus 1 by 2n, it is n into 2x minus 1, and it is after that it is 1. Okay, so we are seeing here these all the functions f1, f2, and f3 and so on, these all are moving towards this. Okay, okay, so this is clearly a Cauchy sequence. We can observe, we can prove it. So this is a Cauchy sequence, and we can also see that it converges to where it converges. It converges to, okay, okay. So it converges to where? It converges to fx, where fx is what? It is 0 from 0 to half, and after that it is 1. And clearly this is a step function. That means it is discontinuous at half. So we got a sequence of functions which is Cauchy sequence but not convergent in C01. So the C01 is incomplete metric space. Okay. So next one is note that if S be a non-empty subset of metric space XD, then if we take any element in closure of S, okay. So what is closure of S? Closure of S is nothing but the smallest closed set uh, of X which contains S. That means it is a set of all closure points of S. It is also intersection of all closed subsets of X containing S. Okay. So uh, this for this S, we have a convergent sequence. We have a convergent sequence xn in S such that its limit is yes. Okay, that means for every element in closure of S, there exists a sequence, a convergent sequence xn in S which converges to small s. Okay, so you can prove it easily. So now we have a question: is subspace of a metric complete metric space complete? And second question is continuous image of a complete metric space complete? So the second question is almost discussed by Dr. Bipul Kakkad in some other sense. So I'm not going into it. First answer of first question is no. Okay. So what is example? Example is just set up rational number, which is the subspace. You know what is subspace of a metric space? Any subset of a metric space that can be equipped with a metric induced by the metric on a given metric space, that is called subspace. Okay, so this Q is subspace of R. R means set of real numbers with usual metric. Okay, which is not complete, but close interval 0 1 is complete subspace of R. Okay, so we have a proposition that when a subspace of complete metric space is complete. So in a complete metric space, a subspace is complete if and only if it is closed. That means if we are taking a closed subspace of complete metric space, then it becomes complete. Or if there is a subspace which is there is subspace of a complete metric space which is also complete, then it must be closed. Okay, so here is proof. How will we prove? Proof is that if we take A to be complete subspace of F, we have to prove that it is closed. So if we consider its closure, what is its closure may be equal to A. If its closure is equal to A, then it is obviously closed. So we are done. And if its closure is not equal to A, then we get at least an element in A closure which is not inside A. Okay. So, but we get from our previous observation, we get convergence sequence xn. Okay, in particular, it will be a Pussy sequence in A, such that it converges to small a. Okay, but as we have already considered that A is complete, so this sequence converges in A itself. That means small a is also a member of capital A. Okay, so uh, which is a contradiction? What is contradiction? Since we have already assumed that a is the member of closure of A, but not inside A. This is what contradiction. So this case cannot be happen. Hence, A closure is equal to A, and so A is closed. Now, conversely, suppose if A is closed subspace of X. Okay, so now we wish to show A is complete. Okay, so uh, consider a Pussy sequence Xn in A. If it is a Pussy sequence, okay, so but we know that capital X is complete metric space, and this xn sequence xn is also Pussy sequence in capital X. So it converges to some point, say small x. Okay, so since you know xn is the sequence in capital A. Okay, so the small x is the limit point of capital A. One can easily observe that this small x is a limit point of capital A, and this small x is inside derived set of A, which is clearly contained in A closure. But since A is closed here, so A closure is equal to A. Hence, X belongs to capital A. Okay, so that means what we got? We get that the Pussy sequence action converges in capital A itself. Hence, A capital A is also complete. Okay. So next, next is what? Next is we have a proposition that let XD be a metric space and sequence action. Sequence action is what? This is a 2C sequence in X. Then it is convergent if and only it has a convergent subsequence. I think it was somewhat used by Dr. Bipul Kakkar. So we see its proof here. If this sequence is convergent sequence, then what? Then it is also a convergent subsequence of itself. Okay. Um, I wish to ask Mr. Naman, please stop your video. Okay. Okay. So uh, sequence xn is convergent subsequence of itself. So we are done in this case. Now, conversely, if we have a convergent subsequence x and k of sequence xn such that it converges to some point x. Okay. So now our claim is this sequence xn also converges to x. Okay. So consider epsilon greater than 0. So since this sequence x and k converges to x, so for there exists uh, an element k1, a natural number k1, such that distance between x and k and x is less than epsilon by 2 whenever k is greater than or equal to k1. Okay. Also, this xn sequence xn is convergent. Okay. uh, 1 minute. I think this is not convergent, but what we have considered here, we considered that what is xn? Xn is convergent if it has convergent subsequence. Okay. Okay. So we are doing its converse part. So x and k. Okay. Okay. There is a typo. I think it must be UC. Okay. This is this is UC. Okay. Okay. So since xn is a UC sequence, so there exists a natural number n1 such that distance between xn and xm is less than epsilon by 2 for every n and n greater than or equal to capital N1. Okay. So, but we know that by triangle inequality, distance between xn and x is less than or equal to this much. And note that since x and k is the subsequence of xn, so the suffix nk is always greater than or equal to k. One can easily observe it. Okay. So now choose capital N is equal to maximum of an1 and k1. So what we get? So for n greater than or equal to n, we can see n is greater than or equal to n1 and n is greater than or equal to k1. Okay. So Now, this distance between xn and x is less than, strictly less than epsilon by 2 plus epsilon by 2 for every n greater than or equal to capital M, and in which we have considered m is equal to nk, which is greater than or equal to k, and which is greater than or equal to k1. Okay, so distance between xn and x is less than epsilon for every n greater than or equal to capital N. Hence, our sequence is convergent and converges to the same limit x. Okay. Now we have a remark that a metric space xd is a complete metric space if and only if every 2C sequence in X as a convergent subsequence. Okay, so this is just a consequence of our proposition. Okay, so next we have already discussed isometry in previous lecture. What is isometry? Isometry is nothing but a function from one metric space to another which preserves distance. Okay, so we can see these two examples here. What is the example? Example is the identity function from a metric space X to itself. It is trivially an isometry since it preserves distance. I'm sorry to say that please mute your sorry, please stop your video, Mr. Abhishek. Okay. Okay, now the next example is if y is a subspace of xdx, then clearly y is included in x. That means the inclusion map I from y to x is an isometry. Okay, so this is these are two examples here, and the third one is what? Suppose we are taking Euclidean space Rn. So for any fixed vector a bar in Rn, we consider a map. This is a translation map from Rn to Rn, which sends x bar, vector x bar to x bar plus a bar. So you can observe it that this is clearly an isometry. Okay, it preserves distance. Okay, so I think one thing here I haven't discussed, I will tell you later. It is that okay. So fourth example is consider uh, metric spaces C. C means complex metric space, and R2 with these two both are with the usual metric. So if we consider a function f from which sends x plus I by 2 ordered pair x comma y, so we can observe that it is an isometry. Okay. Fifth example is suppose we have a vector a bar in Rn. So reflection, we consider a reflection with respect to the plane here. This may not be a plane. That means if we are in higher dimension, so it will be generalization of plane also. So uh, the reflection with respect to the plane given by this equation x bar dot a bar is equals to 0. This is equation of a plane passing through. I think it should be origin. Okay, so this map R a bar which is given from Rn to Rn, which is given by R a bar of B bar is equals to B bar minus 2 uh, B bar dot A bar into A bar. That means this is reflection. Okay. So this is also an isometry. One can check it. Okay. So next one is what we have a note that if F is an isometry from X to Y, then it is obviously an injective map. And we have already observed this one, okay, in previous lecture. So one can see that F from X to Fx, that means image of F, okay, it is a bisective isometry. And we can think X as a subspace of Y, okay, in form of its image, okay, or we can also say that X is embedded in Y, okay. So every property which is possessed by X, it is also possessed by Fx also, okay. Next, we have a remark that we know that open interval with usual metric is not complete metric space, but after some, I think there is a typo in the spelling of effort. So after some minimum effort, by adding some members into it, okay, it becomes complete. That means if we put 0 and 1 inside this open interval 0 1, so it becomes closed interval 0 1 and it becomes complete. So we have a question that can we always make an incomplete metric space complete by adding some members into it? So what is our answer? Answer is yes. Okay. So this is the completion of a metric space. Okay. So what is completion of a metric space? So suppose we have a metric space X comma G1, then another metric space YG2 is said to be completion, said to be a completion. That means from here we are assuming that there may be several completions, okay. So completion of metric space xd1 if there exists an isometry f from x to y such that fx is dense in y, okay. So that means what? That means x is embedded in y as a dense subspace, okay. So then we will say that y is the completion of x, okay. Or and why we are taking dense subset? That means we wish to include minimum elements in X so that it becomes complete. So dense, and you know what is dense? Dense means uh, that subset of a metric space is dense whose closure is the whole of X. Okay. So now we have example that the closed interval 0 1 is a completion of open interval 0 1, and R is a completion of set of rational numbers Q. Okay, and completion of a complete metric space is what? Completion of a complete metric space is the metric space itself. And we are not saying this is equal to that metric space, but later we will tell that what will be it. Okay. So but one completion of the complete metric space is the metric space itself. Okay. So now we have a question that does completion of every metric space exist? Okay. And if it exists, does this completion of metric space unique? That means First of all, we are asking that whether it exists or not. And the next question is if it exists, then is it unique? So we have a theorem that completion of every metric space exists, okay, and it is unique up to bijective isometry, okay. So the answer of both questions is positive, and it says that completion of every metric space exists, and it is unique up to bijective isometry. That means if we have two completion of a given metric space, then there exists a bijective isometry between uh, first one to second one, okay. So we have written this statement in another way, another form, that let X be a metric space, then there exists a metric space X star D star and an isometry F from X to X star, such that X star D star is complete and image of F, that means Fx, with D star, with the metric D star is dense in X star D star, okay. Moreover, if this is uniqueness part, if we have two completions of XD, Y and Z, then there exists an onto isometry. It is I think okay here, since if we have an isometry, then it is 1 1 itself. So it is quite obvious to say onto only. Okay. So now a sketch of these two statements. Uh, so we are going to prove first of all its existence. So first proof of the existence. This is modern proof, and it is quite simple. So suppose X naught be a fixed point in the metric space Xt. So for any element small x in capital X, we are defining here f suffix x, a function from x to r, which is defined by uh, fx of y is equals to distance between x and y minus distance between x naught and y, okay. And so one can easily observe that this function fx is bounded function for every x, okay. So how it is bounded. So Ruby, please mute yourself. Okay. Now observe that fx is bounded function. How it is bounded? So suppose we are taking here a mod of fx of y. That means image of y under fx. This this must be less than or equal to yes. This must be less than or equal to mod of distance between x and y minus distance between x naught and y. So using somewhat triangle inequality, we can anyhow manage that this must be less than or equal to the distance between x naught and x for every y belongs to x. Okay, so that means fx is a bounded function from x to r. That means it is a member of dx, where what is dx? Dx is nothing but it is a bounded it is set of all bounded functions from x to r, okay. So note that what is this Bx? This Bx is a complete metric space. This is a complete metric space with respect to the metric d infinity, and which is given by d infinity of fng is supremum of mod fx minus gx, uh, where x belongs to capital X. Okay. So this is d infinity, and with respect to d infinity, this is a complete metric space. This this should be observed by you, and we are not going in detail of itself. Okay. So now also, actually we have written the sketch of proof here. So many things is left to be verified, so you have to verify it. Okay, so observe that phi from x to dx, which is given by phi of x is equal to f of x for every x belongs to x. This is an isometry. How is it isometry? So suppose we are computing distance between the image of x1 and image of x2 under phi. So phi of x1 is nothing but fx1, and phi of x2 is fx2. So distance between fx1 and fx2 is what? This is nothing but supremum of the set mod fx1 of y minus fx2 of y, where y is inside x. Okay, so we can compute it, uh, and we can see that this is nothing but supremum of mod distance between x1 and y minus distance between x2 and y. Okay, so you can easily check that this supremum will be nothing but distance between x1 and x2. Okay, so I think while checking it, you need to use triangle inequality also. Okay, so so the distance between fx1 and fx2 is nothing but distance between x1 and x2 for every x1 x2 inside x. So this phi is an isometry. Okay, so hence the closer. Okay, wait a minute. Yes, okay. Hence, closure of phi x. That means image of phi is what? This is a collection of all fx, uh, and this is this closure is taken in is the subspace of bx. Okay, so our claim is this closure of phi x is completion of x. Okay. So for which we have to just observe two things. First one is this closure of phi x is complete. Okay, and second one is closure of sorry. Second one is phi x is dense in closure of x. So since every set is dense in its closure, okay, by definition. So phi x is also dense in its closure, and we have already observed that a closed subspace of complete metric space is also complete. So since phi x is closed here, wait a minute, sorry. I think phi x is not closed. So okay, so closure of phi x is closed. Okay, closure of phi x is closed. So it is being closed subspace of bx. It is also complete. So we got completion of xg. Okay, so we are done here. Now proof of the second proof of this existence of completion is It is Cantor's construction. Okay, and in this construction, we get an algorithm. So algorithm to construct completion of a metric space. Okay. So suppose we are considering set of all QC sequences in X. So now define a relation on Cx by um, we are defining this relation that any two QC sequence is related if and only if uh, the limit of distances between corresponding terms tending to zero. Okay, so that means if we have two sequences xn and yn, and if we are taking limit of distance between xn and yn, if it goes towards zero, that means the limit is zero. Then we say that these two sequences are related. Okay. Now for this relation, uh, yeah, for this distance in X, one may observe that following these things. First one is what? First one is the limit of distance between xn and yn as n tending to infinity. It always exists for any QC sequence xn and yn. It always exists. Okay. So you have to observe it, you have to prove it. And second one is what? If distance between xn and yn goes to zero as n tending to infinity, then the first sequence xn is convergent, which converges to some say some limit L. Then the second sequence will also converge to the same limit L. Okay, so it is also quite obvious, I think. Okay. And third one is what? Third one is if limit n tending to infinity distance between xn and yn is equals to zero, and limit n tending to infinity distance between zn and tn is also zero. That means there are four QC sequences, and distance between first and second is tending to zero, and distance between third and fourth is also tending to zero. Then we see that distance between first and third is same as limit. The limit of distance between first and third is same as the limit of distance between second and fourth. Okay. So we can easily observe these things. So now next one is the relation. This relation tilde is an equivalence relation on Cx. This is also quite easy, and it can be proved using the previous observations from 1 to 3. Okay. So you have to prove it. I am not going to prove here. Okay. So now consider the quotient set. We are as we know that if we have an equivalence relation on certain set, then it gives its partition in the form of equivalence classes. So a set of all equivalence classes is called quotient set. So we are considering here quotient set in which the elements are sequence QC sequence X, that means sequence class of QC sequence xn. Okay. So what is equivalence class of QC sequence xn? This is the xn bracket xn bar. This is collection of those QC sequences which is equivalent to or which is related to xn. Okay. So now we are denoting here this cosine set by x star. So now we are defining a distance function on x star, which is given by this limit n tending to infinity, uh, distance between xn and yn. And we have to check that this distance, this d star is well defined, and also it is a metric function. Okay, so we have to check it. Okay, so I'm not going into detail, but you can check it. So now consider the function phi from x to x star. So how phi is defined here? Phi is defined in the way that we are sending small x to the equivalence class of bracket x. And what is bracket x? Bracket x is the constant sequence x comma x comma x and so on. Okay, so we are sending x to the equivalence class of the Pussy sequence uh, x. Okay, so we can also easily verify that this phi is also an isometry. Okay, we can verify it. And why are we sending it this ex to this constant sequence? As if we suppose we are checking a non-constant sequence, and which converges to non-constant Pussy sequence, which converges in the same set X. So suppose it is say y. Okay, so if it is converging to y, then this sequence is equivalent to the constant sequence y. Okay, we can check it. Okay, so since the distance between the given sequence and the constant sequence y, as n tending to infinity, it goes to 0. So these two are equivalent. So their equivalence classes will also be same. Okay, so we can observe here that phi is an isometry. Okay, so I don't know. Okay. I haven't verified it, but you have to verify that phi is an isometry. Okay, so we can now check that uh, this x star d star is a complete geometric space, and second one is image of phi, that means phi s is dense in x star. Okay, these two are big thing. You have to check, and if it is checked, then we can say that this x star d star is a completion of x and d, x comma d. Okay, so uh, we have omitted many things to verify. Okay, so you have to verify it. Okay, now this construction, Cantor's construction, is an easy method to show that R is a completion of set of rational number Q. That means uh, from Q we can construct R using this Cantor's construction. Okay. So now we come to the proof of uniqueness of completion. So suppose we have two combinations of metric space X, G. So then we have two isometries F from X to Y and G from X to Z, such that Fx is dense in Y and Gx is dense in Z. Okay. So now we have to find a bisective isometry from Y to Z. Okay, so if we take any element y inside capital Y, So clearly fx is dense in y. So we have a sequence, we have a convergent sequence in fx which converges to y, but the sequence in fx is of the form f of small xn. Okay, so we get a sequence xn inside capital X such that its image is a convergent sequence inside fx which converges to small y. Okay, so now we can easily check that if we are considering f inverse composed with G, this is a uh, this is a map from fx to gx, and it is composition of two isometries. Okay, and two, I think, two bijective isometries. Okay, so it is composition of two bijective isometries. Why it composition of two bijective isometries? Since f is an isometry. Okay, from x to y. So f is a bijective isometry from x to fx. So its inverse exists. Okay. So f inverse is also a bijective isometry from fx to x. Okay. And similarly, G is also a bijective isometry from x to gx. Okay. So a composition of two bijective isometries is again a bijective isometry, so we can check it. Okay, so next is what we get a QC sequence GXN, that means it means image of sequence XN under the map G. This is a QC sequence inside GX. Okay, which is a subspace of Z, and it converges in Z. Why it converges in Z? Since Z is already complete. Okay, so Z is complete, so it this QC sequence converges in Z. So suppose it converges to small z. Okay, and if it converges to small z, okay, so we can define, we can get, we have an image of a small y, which is obvious to send to small z. Okay, so phi is a map. We got phi is a map from y to z, that this small y goes to small z. Okay, so again we can check it. This phi is a bijective isometry. You have to check it. Okay, again. So hence the xd has unique completion up to bijective isometry. Okay, so many thing is done here, but many more things are left to check. So I will say that please verify all those things and fill the gap. And many other things are also there using complete metric space. So suppose we have Cantor's intersection theorem and Bayer category theorem also. So it will be done by Mr. Ramji Pandey in next lecture. So I should stop here. Thank you. Thank you very much.
थैंक यू डॉक्टर लक्ष्मीकांत। राम जी कोई
आवाज नहीं आ
सवाल
रही
है?
जी सर।
आवाज आ रही है?
जी सर, जी
हाँ, राम जी कोई सवाल है क्या?
सर एक क्वेश्चन है अजय यादव का।
जी हाँ।
सर
एक
up to uniqueness is bijective isometry unique?
up to uniqueness
is bijective isometry unique?
I don't understand
क्या
what is
बोल
up to isometry, up to unique. Yeah, I don't understand its meaning. So, but I think I should say this bijective, this construction of bijective isometry is done in unique way. So it is unique in some sense. Okay.
There is a question from Shubham Jaiswal. Sir, please
Mhm.
explain how we think such type of examples and then what strategy that we follow
Which
for
type of
showing any
example?
metric is not complete.
For showing any metric which is not complete. Okay. So if we wish to show that a metric is not complete, we just consider, we just we have to find Pussy sequence which is not convergent in that set. Okay. Next.
Hello, sir.
Subham.
Hello. Sir, in the example of C01, where you take integral 0 to 1 and then you consider a sequence of functions.
Mhm.
Uh, so, sir, my doubt is how can
Mhm.
we think s- such type of sequences in general
Okay.
other than this
Actually, huh? Actually,
means
we just have to construct such example. We have to create this example such that this should be a Pussy sequence, but which doesn't converge in that given set, given metric space. So we just have to construct it. Okay. So there is no any method how to construct, but just we have to create these examples. Okay. So there are several
uh,
examples. I have taken one example. You can find another examples also, which is Pussy sequence but not convergent. Okay.
yes, sir, but the doubt is
That-
you have
Mhm.
chosen this example
Yeah,
to
this is
show
one
that.
example.
So how how will you think that this how what I am choosing, then it is a
Okay,
Cauchy
okay,
Cauchy sequence but not
okay.
convergent.
Yeah, of course. If you
I am
have,
asking that.
yeah, of course, there is no such method. But if you are thinking in about these things, so you have intuition. So if we will take this example, this may converge to the some given point, and if we have to create this such type of sequence which whose limit doesn't fall in this set, we just have to think about it, just construct it. Okay. So there is no such method, I think. Okay. Any other question?
Okay, thank you, Dr. Lakshmikant.
Thank you, sir. Thank you so
इतनी व्यस्तताओं के बावजूद ऑर्गेनाइजिंग सेक्रेटरी साहब ने लगातार जो है व्याख्यान दिया और हम सभी जो है धन्यवाद करते हैं और 1 बजे हम फिर मिलेंगे राम जी पांडे सर का व्याख्यान सुनने के लिए थैंक यू ऑल ऑफ
थैंक यू सर। लेकिन एक्चुअली ये हैंड रिटन नोट्स मुझे लिखना पड़ा, बट मुझे लग रहा था कि मैं बोर्ड पे करता तो और अच्छा हो पाता, बट कुछ दिक्कतों की वजह से मैं उसको नहीं कर पाया, तो
नहीं
सॉरी फॉर
बहुत
दैट।
ही बढ़िया रहा, कोई दिक्कत नहीं है और इसको हम फिर बेहतर करेंगे। बोर्ड बिल्कुल बेहतर होता है,
जी सर।
क्लासरूम टीचिंग का विकल्प नहीं है कुछ,
जी सर।
लेकिन फिर भी बहुत बढ़िया,
ओके
गुड
सर,
जॉब,
थैंक
थैंक
यू
यू
सो
ऑल
मच।
ऑफ यू।
थैंक यू।
राम जी एंड कर दीजिए मीटिंग।
जी सर।